Yep, thank you very much. It's a great pleasure and honor for me to be actually at Berkeley this semester and being hosted by this geometry of polynomials where I'm learning much more than I'm giving, but it's quite a fascinating subject, and I will mention it at one point in connection with this lecture. The title of my lecture is Randomness in Number Theory, but in many of the flyers it was announced as the limits of proof. So I will try accommodate both. I know very little about the limits of proof, but my advisor Paul Cohen knew quite a lot. So let me start with him, and I'll quickly get past that. And at that point, anybody who really wants to see about limits of proof might want to leave. As I say in the airlines, if you aren't on the flight to San Francisco, now might be a good time to leave. I'll tell you when to leave. Okay, so I went to Paul Cohen 2 years before he passed away. He wrote a paper on Skolom's method and the pessimism about proofs in mathematics. And he writes a number, it's a short paper, but let me read it out to you, the key relevant points. He certainly was interested in the theory of numbers in the second half of his life. And he says, with like we reach a contradiction, he's explaining Skolom's method, and thereby prove something. But suppose one asks an unnatural statement about primes, such as the twin prime question. I'll return to what that is in the lecture. Perhaps on the basis of statistical considerations, we expect the primes to satisfy this law. But the primes seem rather random, and in order to prove that the statistical hypothesis is true, we have to find some logical law that implies it. Is it not very likely that simply as a random set of numbers, the primes do satisfy their hypothesis? And then he continues explaining about limits of proof, and he says, therefore, my conclusion is the following. I believe that the vast majority of statements about integers are totally and permanently beyond proof in any reasonable system. And that would include allowing more axioms, so getting around Gödel's incompleteness theorem. Here I am using proof in the sense that mathematicians use the word, so he's being somewhat vague. Can statistical evidence be regarded as proof? I would like to have an open mind and say, why not? If the first 10 billion zeros of the zeta function, I'll define it today, lie on the line, whose real part is equal to a half, what conclusion shall we draw? I feel incompetent even to speculate how future generations will regard numerical evidence of this kind. In this pessimistic spirit, I may conclude by asking if we are witnessing the end of the era of pure proof, begun so gloriously by the Greeks. I hope that mathematics lives for a very long time and that it does not reach that dead end for many years to come. So that's quite a downer. And if you want to leave now, then leave. I will return to it at the end. I'm going to talk about randomness, and he's already raised two questions that were dear to him and are dear to me, the twin prime problem and the Riemann hypothesis, and both are intimately connected with randomness, as I want to try explain. All right, so the thing I'm trying to contrast is the theory of numbers, whole numbers, prime numbers, arithmetic operations, modulo prime numbers, Diophantine equations, and then something that I will try explain. There's a movie about the proof of Fermat's last theorem where the interviewer goes to each of these experts and asks, can you explain what a modular form is? And nobody tries except Barry Mazur, who seems to pull it off. I will try today and probably fail like everybody in that movie, if you haven't seen it before, that is. But I'll give you some feel what they are and why they're special. And in probability theory, which people have, I think, much better intuition about, they are random objects, but the relevant ones for the theory of numbers are random geometries, random matrices, random polynomials, random walks on groups, and even percolation. And in probability theory, you look for universal laws, like the Gaussian, and the topic is to try explain the role and the interplay between number theory and probability theory. So I want to put forth a dichotomy, which in the theory of numbers, this obviously will have exceptions, but in the theory of numbers, either a problem has some rigid structure, often not very clear what it is, but when you find it, you certainly know you found it, or the answer is very difficult to determine and looks like it's random, and I'm going to give you examples of this. And then the idea would be that you try to prove that randomness has kicked in, and that turns out to be much harder than proving structure. We're good at occasionally understanding some structural things. So the randomness feature can be quite unexpected. The distribution might be from somewhere else where you weren't expecting, and that would be very telling. Establishing such a law is usually the very issue. So sometimes when the law is obvious, say it's the central limit theorem clearly in action, then it's just a matter of establishing it for something which is very explicit. And there are implications in both directions. So if you, of course, understand the law, you'll understand the phenomenon that you're looking at very well. And the fact that explicit arithmetic Diophantine problem can behave very randomly can be a source of something very useful. So in the old days, Hardy used to had there's a standard quote of Hardy that says that number theory is the field. Gauss too. Gauss viewed number theory as the queen of mathematics. Hardy felt that mathematics is being used very badly during the First and Second World War, and the one subject that will never be used is number theory. Of course, he didn't predict the internet and the computer. And so predictions are very dangerous from that type, or from that point of view. We could ask about producing pseudo-random numbers. That would be obviously the starting point of making something random through number theory, but I want to start with something that's even more basic. So let's take the number pi, which I think is about that to so many decimal places, but if I gave this lecture on Pi Day, maybe somebody would be complaining somewhere. Is pi normal? A normal number is a number which has the right number of digits that a random number should have. So the number of ones in its decimal expansion should be 1/10 of them. The number of twos should be 1/10 of it. And there's no doubt that if you look at the statistics of the expansion of pi, it's random. It's normal. We have no idea how to tackle such a problem. So this is I'm going to give 4 examples of what I'm talking about. There are many more. I'm going to give 4. And the first one is this: is pi normal? We know so little that I don't know anybody who even would try attack this problem. The kind of thing we know is we can prove some little iota of randomness, meaning we know the expansion is not periodic. It's not completely structured. In other words, pi is irrational. We also know something much deeper. It's transcendental. It doesn't satisfy any polynomial equation with integer coefficients. That's one of the finest achievements in mathematics by Lindemann. Still one of the finest achievements. So the kind of thing that we can prove about pi is this little iota towards showing that it's a random number. And even that is considered, as I say, a major achievement. All right, so I'm going to leave that because I have nothing to say about it, except that clearly you will see features like this. We'll have something, is it random? And then the whole thing is to try to find methods to show things are random. And Paul Cohen was referring to that. He said, when we prove something, we really have to have some structure in order to make a conclusion. It's very hard to prove something is random. In fact, nobody knows how to make anything that's genuinely random, as you know. All right, so my second example is I'll have 3 more examples, and the second one is a large chunk of the lecture. And it'll be about primes and quadratic Diophantine equations and arithmetic, the randomness in arithmetic. But let me start with primes. So the randomness that Cohen was saying when he was saying the primes look like they're random, well, let's just remind ourselves what primes are. They're numbers which are only divisible by themselves and 1. The number 1 we don't consider to be a prime, and there's a standard way of making a table, the sieve of Eratosthenes, where you look at the first number, 2 is prime, then you strike out the multiples of 2. You look at 3, 3 is prime, you strike out the multiples of 3. In fact, it would be better if I struck out here with multiplicity, and then I could ask a question that'll come a little later, but I was a little lazy, so I just struck out what I struck out, and what's left behind are the primes. And those are the primes, and you look at them, and mankind has looked at this, and every mathematician from a certain older generation, from Euler to Gauss, have all made statements that we don't, and Hermann Weyl, that we don't understand the randomness in the prime numbers. There's no sort of, where's the next prime going to come? What do we know about it? But they are structured in other way. We made the construction of them is very simple. The twin primes that Cohen mentioned are numbers which differ by 2. And while there has been progress on this kind of problem, we're still very, very far away from twin prime because there's a fundamental difficulty there connected with what's called parity. And I'll describe this parity to you a bit later. So it does, as Cohen says, it does look rather difficult to prove the twin prime in our present understanding. But I'm not that pessimistic as he is about anything like this. All right, so those are the primes. Are they random or structured? Let me remind you what the prime number theorem is. So you could ask, how many primes are there less than a number x? So take an integer x, how many primes are there less than x? So that is usually denoted by pi of x. That pi is not that pi. So you could ask, how big is pi of x when x gets big? And there is a first approximation, which is one of the achievements of the 19th century. And that is that as x goes to infinity, pi of x is roughly x divided by log x. There are infinitely many primes, and their density is roughly 1 over log x. And that's the famous prime number theorem. By the way, in this lecture, I'm not going to give credit to anybody. I will have a slide at the end, which is credits. So that's an unusual way of proceeding in math, but let me do it that way. Otherwise, it would take some of my time. All right, so that's the prime number theorem. And I want to explain to you the difference between what I view as a structured problem and a random problem. So let me take an odd prime p, think of a very large odd prime p. We know there are many of them now. And let me take the following sum called the Gauss sum. So it's the sum of e to the 2 pi I. Now the exponential is just a trigonometric function. E to the 2 pi I of an integer is 1. So when I write the sum down from x equals 0 to p minus 1, I'm summing over all the x's. The only thing that's important is the remainder of that fraction when I divide by p. So it's going to be very important, so let me spend a second on that. If I look at the remainders of integers when I divide by a prime number p, and this does use as a prime number, I look at just what remainders you get. I can do the same arithmetic that you normally do. You can add numbers, and you can multiply numbers and just keep the remainders. And they satisfy the usual rules that you're familiar with in arithmetic. And you can even invert numbers, and that's equivalent to p being a prime. And so this forms what's called a finite field. And what Gauss is writing down there is a sum of complex numbers. There are p of them. E to the 2 pi I of something real is of modulus 1. So you're adding p numbers. If they were random, and this is going to be important, this is my first connection with random. If I add n numbers, which are modulus 1, and they're random, they should cancel to about square root n. So the size of that sum you might expect to be square root in size. It's an easy exercise to square g and collect terms, and you'll find that g squared is p, so g is in fact in absolute value square root p in size, or minus p, depending on whether p gives remainder 1 when divided by 4, or whether p gives remainder 3. So this was well known, and Gauss was very interested, as were many other people, in which sign is the square root. Is g plus square root of p, or is it minus square root of p? And in the case that p is congruent to 3 mod 4, is it I times root p or minus I times root p? They're two square roots of a number. And the sign of the Gauss sum is something he worked out. And if you think that he didn't think this was important, this is what he writes about it to his friend William Olbers and his correspondent LeBlanc, who's secretly Sophie Germain, who had been studying his work and who did some remarkable work herself. She went under a pseudonym. And he says that this shortcoming, he's talking about trying to compute. He said that what he was trying to do in his Disquestionia Arithmeticae, which is his main book on number theory, what he was trying to do, he achieved, and I'll show you what he achieved in a minute. It's one of the great theorems that we try to emulate generalizations of. Anyway, he proved that, but along the way, there's a question of which square root is that Gauss sum. And I've looked at this, he says, hardly a week has passed during the last 4 years where I haven't made an attempt in vain to untie that knot, especially vigorously during recent time. But all of this brooding and searching in vain, sadly, I'd put the pen down again. Finally, a few days ago, has been achieved, but not by my cumbersome search, rather through God's good grace, I'm tempted to say, as lightning strikes, and he carries on, and he marvels that he finally computed the sign of the Gauss sum. However, my astronomical work should not be completely neglected at this time. In other words, at the same time, he was developing his work in astronomy and Gaussian distributions of heavenly bodies, and this to him was still a hobby, maybe. But you can see the joy with which he found the structure. That's a structured answer. If you go and you experiment with it, you'll find which square root it is, but proving it is by no means easy. It's very closely connected, though you don't need to know it to prove this theorem, to his famous reciprocity. So this is a good example of what I mean by structure. So if you take two prime numbers which give remainder 1 when divided by 4, both, if I look at arithmetic mod p and arithmetic mod q, those are fields, and I can ask whether p has got a square root modulo q in that field, and that's if and only if q has a square root modulo p. This is highly non-obvious. It was known experimentally before Gauss. Gauss was the first to prove it, and there are many proofs today, and they are the kind of thing that drives subject. So class field theory is a subject in number theory which is a grand generalization of this, and the grandest of all generalizations of the reciprocity is called Langland's reciprocity in the theory of automorphic forms, which I said I will try to find for you. One example. All right, so that's an example of the Gauss wanting to find the square root. I should say that if you take the cubes, e to the 2 pi I x cubed rather than x squared, then there's no formula for the sign, and they are random. And that was first, there were false conjectures, but the first realization of that they're random was when von Neumann was running his maniac computer with Goldstein in the 50s in Princeton, checking what the signs of cubic Gauss sums are, and they are random. And that was proved in the 70s, that they are random, that is equidistributed, just the simplest version of random. So this is something very special, the sign of a quadratic Gauss sum. All right, let me stick to arithmetic mod p, because that's a place where we'll see randomness kick in. So suppose I advance through the numbers x from 1 up to p. Then x inverse exists. So 1 inverse is 1, 2 inverse is p minus 1 over 2, but quickly you don't know where x inverse is, and it seems to jump around randomly. And if you look at it numerically, the map x to x inverse modulo p, if p is a very large number, looks very much like a random involution of a set of p elements, numerically. So the arithmetic operation of inversion, when you look at them, first order them by linearly, and then look at the inverses seem to come down randomly. And one measure of whether that's true is to take the correlation between, A is just a parameter there. So I look at x mod p, and then I look at x inverse mod p and exponential. And if they don't know about each other, then they should be random numbers of modulus 1, and that should cancel to about square root of p. I keep on coming back to that theme. Now, SAP has no easy formula. Unlike the Gauss sum, there's no easy. The size is not root p, but the deepest theorem in this subject is that that's less than or equal to 2 times root p. So, and that's a sharp bound. So it's clearly not quite random, because random numbers don't cancel to exactly square root n. They get a little bit bigger than square root n. There's the law of large numbers. But they have this feature. And this is already something very deep. This follows from something called the Riemann hypothesis, which is a theorem. It's an analog of the real Riemann hypothesis, which I'll describe to you. I will not describe this Riemann hypothesis. But it's an example of the Riemann hypothesis showing something's random in some statistic. So that's a very deep fact, that's at most 2 root p. And the fact that the numbers, when you take them from 1 to p, that the inverses are random, are something that can be exploited and have been exploited heavily. They are a source of pseudo-random constructions. And since one of the things that's discussed in this polynomial here, I'll return to that in a minute, is Ramanujan graphs, let me give you examples of these. So in computer science, there are graphs that are called expander graphs. They are highly connected but very sparse graphs. the fact that something could be highly connected and sparse at the same time is obviously extremely, they fight each other, and it's obviously useful if you want to connect things with few wires or you are trying to do some other efficient construction. So let me give you a construction, and my intuition as why this construction works is really because the operations of arithmetic are random, as I just described. And you need this division. You need the operation which is a division, which was x goes to 1 over x, and you'll see it happening here with 2 by 2 matrices. So I'll take a number, a large prime number, which is 1 mod 20. You might say, gee, how do I know there are many primes which give remainder 1 when divided by 20? That's something we understand. There are as many such primes as there should be. And I take such a prime, and then I compute the square root of minus 1. By the way, that can be done quickly. I compute the square root of minus 1. Why is there a square root of minus 1? Well, that reciprocity theorem of Gauss tells me. And I choose one of the square roots. I'll call it I. And then I compute the square root of 5. There's a square root of 5 modulo p for the same reason that Gauss gave us, that reciprocity. And now I write down 6 matrices. 1 over beta. Beta is that square root, either of the square roots of 5, times this 2 by 2 matrix whose entries are in the arithmetic modulo p. I have 6 matrices written down there explicitly. Now take all the matrices, 2 by 2 matrices of determinant 1. If you check, if I multiply this out and divide by beta, the determinant of that will be 1. Those matrices all have determinant 1. And the product of 2 matrices of determinant 1 is determinant 1. And this is a finite set of matrices of determinant 1. And it goes by a very fancy name, SL2, the 2 by 2 matrices of determinant 1, with entries in this finite arithmetic. So there are about p cubed such matrices. And now I'm going to make for you an explicit, fantastic graph. I'm going to join each matrix in the 2 by 2 matrices to 6 neighbors, where I multiply that matrix by these 6 matrices, and I get a graph which is 6 regular, meaning each vertex has got 6 guys coming out of it. And this is a graph which has fantastically strong expansion properties and is a basic building block for many things. That's a 3 regular Riemann graph. There are only finitely many 3 regular Riemann graphs that you can fit in the plane. They can't be put in the plane, so that's the biggest one I know on the left, on the right there. This is an example of the graph I was making for you over there. It's got an arbitrary number of vertices, and it's extremely highly connected. I'm going to show you what that means in a second. So we can make these graphs very explicitly, and the reason they're behaving as if they're random in certain senses is because of this Riemann hypothesis in the function field. All right, let me tell you some of the properties these graphs have. They obey an optimal spectral expansion. So if you measure what you mean by highly connected, these are optimal in every sense, but primarily in the spectral sense. The graphs are not quite, they can't be, this will be an indication that we have a mixture always, a bit of randomness and structure. It is possible to navigate. So one of the consequences of being an expander is that any 2 vertices of this graph have a very short path between them. And then it's quite natural, could you find that short path? And the answer is, you can find the shortest path between 2 elements in the graph if G and H have the property that G inverse H is a diagonal matrix. Remember, the vertices in this graph happen to be 2 by 2 matrices. So I can ask that question. And so for many of the vertices, there is an algorithm to find the shortest path. On the other hand, if you want to get between any 2 points, that's NP complete. So that shows these graphs are quite complicated. That means that if you can solve that problem of finding the shortest path in this very simple graph between any 2 points, then you can actually solve any NP complete problem. In fact, you can reduce this problem to what's called the knapsack problem that Richard Kopp showed in his very early works on NP completeness as being one of the equivalent hard problems. So this is a very simple problem, and the fact that shows you there's a lot of complication here because you can't navigate optimally, but you can navigate 3 times longer than the optimal, which makes this extremely useful. So these are examples of randomness in arithmetic being used to achieve something which is extremely useful. I want to emphasize again that it's the Riemann hypothesis that tells you that every 2 points have a short path between them. It doesn't find you the short path, but it tells you that they are short. And it tells you many other statistical properties that come from eigenvalues of certain operators which are connected with the Riemann hypothesis. The construction that I gave you there works if you have a 6 regular graph, and it'll work if you want to have any graph. You can make a similar construction. If the number of vertices is a number of elements in a field plus 1, a prime power plus 1, elements in a finite field plus 1. So nobody knew how to make a 7 regular Riemannian graph of arbitrary large number of vertices. And I would give lectures and say that without number theory, you'll never do it. But you should never say such things, because that was one of the achievements that led to this polynomials here, where Riemannian graphs of any degree were constructed. And what replaces the Riemann hypothesis, there's a very clean thing that replaces the Riemann hypothesis, is the Lee-Yang theorem from statistical physics. It's playing the role of the Riemann hypothesis, which is one ingredient in the proof, and the other big ingredient in the proof is interlacing polynomials and hyperbolic polynomials. And it's a combination of those two that allows for the construction of Riemannian graphs, bipartite, mind you, of any degree. So that's a bit of a blow to me, because I would have liked to think the only way you can do it is with the theory of numbers. Apparently that's not true. There's nothing wrong with the number theoretic graphs. They're far better, they're easy to make, and you can use them. The same set of ideas, by the way, which has to do with all this has to do with a quadratic Diophantine equation and the theory of modular functions, allows you to construct optimal quantum gates. So if anybody ever builds a quantum computer, now I'm not going to put any bets on whether somebody's going to build a quantum computer, but suppose somebody builds a quantum computer and you want to actually write a program. And in fact, you can buy a quantum computer from IBM, I understand now, and it costs $130,000, and it doesn't do much, but you could be the first owner of a quantum computer. And their program is written using the gates I'm about to give you over here. And these gates rely heavily on the same mathematics and the same solutions and the same randomness and the same navigation. So the difference between a classical and quantum computer, in a classical computer, every bit is a 0 or 1. And in a quantum computer, a single qubit is a vector in C2 of length 1. And that, how you achieve that is, of course, another matter. But that's the theoretical side of quantum computing. If you have n bits in a classical computer, it's just 0, 1 to the n. In the quantum computer, it's C2 tensor to the n of these vectors of length 1. And a 1-bit quantum gate, the only thing you can do with when you're writing a circuit for a program is you can take a bit and you can switch it on and off. There's only one thing you can do, and that's one of the basic operations you should have in your pocket. And it's denoted in circuit theory with this funny thing like that. In quantum computers, because if I have one qubit is a vector of length 2. And if I want to move it around to another position in order to write a program, I need a 2x2 unitary matrix, which takes me from a vector of length 1 to another vector of length 1. So the gates are 2x2 unitary matrices, which now are 2x2 matrices. Before I had 2x2 matrices, which had entries in a finite field. Now I have 2x2 complex matrices. Physicists like to write dagger, mathematicians like to write star. A equals I is the definition of the unitary group. And a gate, a 1-qubit gate, is just an element in the unitary group, which presumably people are trying to build in the laboratory. If all you had was a 1-qubit, you wouldn't be able to go very far. You need to be able to write a program. You need n qubits. But there's a big difference here. In the one ordinary classical bit, you can just switch on and off. But in a qubit, there's a continuum of vectors of length 1. So if you're going to build a quantum computer, the question is, you're not going to be able to get everywhere, because that's a continuum. You only can get into finitely meeting positions. So the question is, you want a gate set, it's called universal, so that you can approximate any unitary matrix of size 2 to the n by 2 to the n by these basic building blocks. And the main difference in this is the 1-qubit, where if you can already do 1 qubit and then add, for example, here in Boolean arithmetic or Boolean systems, you just add and not. You can write down any expression, and a circuit is built out of that. In a quantum computer, if you already knew how to make all 1-qubit rotations, you just add, and this is what they do in this IBM program, you add this controlled NOT, which is a 2-qubit, which you of course have to be able to deal with any 2 at a time in order to write down a general guide. So a universal gate set, which is, for example, NOT and are in ordinary Boolean arithmetic, the ones that are used are Clifford, which I'm going to show you, plus T. These are just 1 qubits, and the C naught. So the Clifford happens to be the following set of matrices which generate U2, or PU2, that's a technical thing, optimally. So there's the other mod matrix, which is that 2x2 matrix, the phase matrix. If you take these 2 matrices, which are 2x2 matrices, and you look at all matrices you just get 24 matrices. They are the symmetries of a cube. And that's called the Clifford group. And they love that particular group. But if all you had was the Clifford group, you wouldn't have a quantum computer. You must be able to get to everywhere in order to have the power of a quantum computer. So for some reason, I've not been able to find out who first in this quantum, this is in all the textbooks, who first came up with this T gate. But they knew they had to add one more gate to make it dense. And they add this gate T. And when you add that gate T, you'll get matrices which you multiply here. You'll get all of something which is dense in the unitary group, and hence you'll have a universal set. And the remarkable thing is this universal set behaves as if it were random, meaning it covers the group optimally fast, and you can navigate just like you can with the Riemann graphs. And the mathematics that goes to do that is all identical. It's all got to do with quaternions and this Diophantine equation and modular forms and the Riemann hypothesis. This time the Riemann hypothesis of well, for varieties of a finite field is needed to actually prove these gates are optimal. So the moral of the story is I don't think anybody's built a quantum computer. If you bought this quantum computer, they run it classically for many things. You have to dial in your program. I think they might run some part quantum mechanically. But if they ever build a quantum computer, these are a optimal set of gates. And the reason that's working is the randomness of arithmetic operations and Diophantine equations. So I hope that shows you that the theme that I was trying to say is that the fact that something's behaving randomly is can be very powerful to make something explicit which is looking like it's random and maybe doing something very nice. All right, I have 2 more such themes of randomness and number theory, and I haven't explained the Riemann hypothesis. So I will bring it to you in an unusual way. So I want to talk about the parity, and I mentioned in the twin prime problem, there's a fundamental stumbling block, it's parity. The most difficult thing that we have in the theory of numbers, just prime numbers, is the parity of the number of prime factors of an integer. That's already quite secret that a number keeps. So let's look for randomness and structure. So lambda n will be the parity of the number of prime factors, meaning whether the number of prime factors after I factor n into prime powers and count the total number of prime factors, is that even or odd? Just to show you that these things can be subtle, suppose I let lambda 3n be the parity of the parity of the 9 prime factors which give remainder 3 when divided by 4. After I factor n, I only look at the primes which give remainder 3. And the lambda 1n, the parity of the prime factors which give remainder 1 when divided by 4. All right, so I have a table here that you can easily compute for yourself. You just factor each number, 1. I'm only looking at the odd numbers here for simplicity. So I look at 1, 3, 5, 7, 9. I factor 1. 1 is 1. There are no primes there, so parity is 0, so the lambda is 1. 3 is a prime, and it's a prime which is congruent to 3 mod 4. So lambda 3 will be minus 1, while lambda 1n will be 1. And then you compute this, ignore this for a second. This times that equals that anyway. And if you look at lambda 3, it doesn't take much to see that there's a pattern. It just switches from 1 to minus 1, from 1 to minus 1. So that's a case of structure that's staring you in the face. There are variants on this where it's not so obvious. The periodicity of the sequence might be quite long, but we understand that very well. So that lambda 3 is far from random. But lambda 1, which is the number of prime factors which give remainder 1 when divided by 4, there is no pattern, and we believe that nobody will ever find a pattern. And this is the kind of randomness that is plain. We believe it, but I'll show you how hard it is to prove anything towards that being a random sequence. Since lambda 3 is very structured and lambda 1, I'm trying to say, is random, so will lambda n be structured. Of course, if I know this one, I know that one. All right, so how do I measure the randomness? One way is to measure self-correlations of lambda with itself, lambda n plus h. But that's the kind of problem where, at the end I'll say, where Paul Cohen might be saying, maybe that's too hard to actually solve. But actually what we can do is we can try correlate lambda n against sequences which are of low complexity. That is to say, if lambda is very random and f is a very low complexity sequence, and if you're at the Simons Institute, low complexity presumably means computational complexity, but that's not the right notion as far as I'm concerned, because A, it takes you in the wrong direction, and B, if I want to believe that when I'm saying it's uncorrelated, seriously uncorrelated, mean that the average value goes to 0, would mean that a low complexity sequence can't mimic the parity, would mean that you can't factor quickly. If you can factor quickly, then we're out of business here, because I could take f of n to be lambda of n, and if you can factor quickly, then certainly that's not the right notion of low complexity. So I'm a big believer that you can factor quickly, but let me just leave it at that. So the right way, or a better way, is to measure the low complexity dynamically. You can measure complexity of a sequence observed in a dynamical system by the entropy of the system. And there's a nice conjecture here, which is that lambda is random in the sense that lambda n times fn will go to 0 for any deterministic sequence fn. That is one which is of low complexity in the sense of 0 entropy. And there's tremendous progress on this. And I would like to point out that many hard problems about the theory of primes involve just showing more randomness in this conjecture. So the sequences for which you land up proving this conjecture are all 0 entropy, all are deterministic, but they are more complicated. The set of such dynamical systems is very complicated, and so each time you prove a new version of that, you've learned a little bit more randomness about lambda. So for example, if f of n equals 1, that's the most deterministic sequence, this goes to 0 is completely equivalent to the prime number theorem. And if f of n is a rotation, this is something that's used to prove the every odd number is a sum of 3 primes. Okay, I should tell a joke. You might ask, is the prime number, is the twin primes, which I even put there, is that an interesting problem? Well, any high school student who sees that, I don't see any high school students, but you would recognize that and you will want to know the answer. Whether it's useful or not, no, I don't think it's got any use, but it's a compelling problem. So there's a famous story of Lev Landau to show you that this problem, from some point of view, may not be so natural. Lev Landau, a very famous mathematical physicist at the Landau Institute, but it was the Steklov Institute at the time, asks one of his friends, he's a young postdoc, why is that guy Vinogradov, who was a nasty guy, why is he our boss? What did he prove? So he said, oh, you don't know? He proved the Goldbach problem for 3 primes. So he says, what's that? So he says, oh, every odd number is a sum of 3 primes. So Landau says, what? How I learned about primes in high school, I thought you're supposed to multiply primes, not add them. It is not a natural problem, but the methods to prove it, they are great. So some of these problems, and I'll return to them, are not natural. The next one is very natural, maybe not stated this way, but stated in the way I'll state it in a second. And that is, suppose I look for a quantitative version of the fact that summation lambda n up to n, I told you, is divided by n goes to 0. That's a prime number theorem. Well, if lambda n is really random, and you look at little n up to capital N, How many numbers have an odd number of parity and how many have an even number? The difference should be at most square root n if they were random. That's always the random model. And this is tautologically equivalent to what's called the Riemann hypothesis, the real Riemann hypothesis. So it's very easy to describe the Riemann hypothesis to you. It's that statement. And all you have to do is prove that. But this offers no attack on this problem, and it doesn't look a natural problem from this other than that parity is random. I think I have to do justice and tell you what the Riemann hypothesis is. So if you don't know what a complex function is, you can ignore this part. So you have a series n to the minus s. In the subject, the complex variable is usually denoted by s, not z, after Riemann. And this has an analytic continuation and functional equation. It's defined for real part of S. And its connection to primes is the unique factorization into primes. So that product is that sum. And Riemann discovered this amazing thing that if you multiply this function by elementary functions, a gamma function and exponential pi to the minus s over 2, then this function has the functional equation s into 1 minus s. And it may be not so well known, but he checked the first few zeros himself. I should say that later people used computers. Turing, one of the very first, one of his dreams was to show the power of the computer in disproving the Riemann hypothesis. And Riemann computed the first 3, Titchmarsh by hand maybe the first 10, and then he had a lot of people work for him to compute up to about 100. And of course Turing could go to a few thousand. And today we know the first, as Paul Cohen said, the first 10 to the 10 are on the line a half. And so we write the zeros as a half plus I gamma, and we find them. The first zero is very high up. This was a very painful thing for Riemann, so he struggled to find it, actually. So the question, from my point of view of randomness, is what do these zeros behave like? Do they behave as if God is throwing down random numbers there? Or maybe there's a much more telling distribution. So this is where I was telling you that occasionally the distribution is quite shocking. It's coming from somewhere else. And it turns out if you look at the zeros of there's no formula, so maybe they're random. And it turns out they are random numerically. They follow perfectly the rules of Gaussian unitary ensemble. The spacing distribution of the large n by n unitary matrices when n goes to infinity, this seems to be a perfect match numerically. It suggests, it's very suggestive that the zeros are somehow eigenvalues or energy levels, which of course is something that inspires people to think about how you might interpret them and how you might prove this hypothesis. It turns out that the zeros of any L function follow this universal rule, and one can, in this function field setting, prove everything. So one can understand where that comes from, and that's because in this function field setting, thanks to the work of Grothendieck, one does have a spectral interpretation of the zeros that is very useful. For those who are real experts, it turns out there aren't 3 families of matrices, GOE, GUE, and GSE, as Dyson has suggested. There are actually 10 families of random matrices that correspond to Cartan's 10 families of symmetric spaces. And only 4 of them come up in number theory, and we understand why, at least in the function field. Here's the 10 to the 16th zero, and it's and it's a billion zeros nearby, and the consecutive spacing between them follows this GUE distribution, which is not easy to compute. Wigner couldn't compute it. It actually is a Paine-Lavey 5. This fits perfectly in physics, where this question was raised by Wigner. The data is so bad that they even have the wrong distribution and they don't even know it, because their data is there's another distribution called the Wigner surmise, which is 1/100th away from this, and it's good enough in practice. But when Odlyzko, who was computing this with the zeros of zeta, for the first time needed to know it exactly, he needed the exact solution of what that curve is. And this kind of fit is plenty good. So the moral here is that the distribution of the zeros is very much random, but it's not random numbers, it's random matrices, and that's something we don't know how to exploit, but it has to be a clue to something. All right, now I have still 5 or 8 minutes. I want to explain that modular forms, which were used in some of the things I was saying, are something very unusual. It's hard to explain why they're so useful, and they allow you to solve problems like Fermat's last theorem and many other things. And there really is a paper that's missing in the literature. There's a famous paper of Wigner called The Unreasonable Effectiveness of Mathematics in Physics. And somebody has to write the paper, The Unreasonable Effectiveness of Modular Forms in Number Theory. And I want to explain to you that one reason I think they are so special is they violate my dichotomy. There are many other things that probably also do, but they handsomely violate it. That is, they are neither random nor structured. They are really a mixture of both. They have both the rigid and random features. They cannot be written down explicitly, yet you can calculate with them to the bitter end. So you can calculate things that you should not really be allowed to calculate using something called the trace formula, and that is what's used in the solution of many, many problems. So they violate this principle. They have got a complexity which allows you to show randomness from structure, and it's exactly that feature that allows you to get your foot in the door. What are these modular forms? They are simply vibrational modes of rigid membranes or geometries. I'll give you one example now. That's what they are. They are vibrational modes. They satisfy certain differential equations on certain rigid geometries. So a good example is just the simplest one. Instead of having Euclidean space and periodic functions like sine and cosine that everybody understands, we get functions that are that much more complicated, modular functions, because they have periodicity under something much richer. So we take the upper half space, all complex numbers with imaginary part positive, and instead of having the geometry be the ordinary Euclidean geometry, in other words, the distance between two infinitesimal distances dz, we divide by y. And this makes the space into the upper half plane into a homogeneous space of curvature exactly -1, as Gauss knew. The shortest distance between any 2 points is a geodesic, which, if the 2 points are on a vertical line, it's that. Or if 2 points are on a hemisphere, semicircle, the 2 points have a unique semicircle which goes through them. That would be the geodesic between them. So this is an infinite space, and the big difference between Euclidean space, where you have the group of motions is just translation, basically. Here, the group of motions are these 2 by 2 matrices, or in general, n by n matrices with integer entries, which act isometrically. They preserve this in the action, which is got division in it, like I was saying in the finite field. Z goes to AZ plus B over CZ plus D. So when you take this group and you take the whole space and you identify points which are on the same orbit, you get a space, and the vibrating modes on that space are the automorphic forms. So they satisfy these differential equations. And from a certain point of view, another reason why automorphic forms sort of defy various principles is that if you were playing billiards in a rectangle, ordinary rectangle, you know exactly where the billiard would go after a long time. But if you play billiards in this triangle, which is what this quotient looks like, with the motion being these geodesics that I just described, this billiard motion is very chaotic. So the fact that you can take a chaotic system and actually write down the eigenfunctions in some form, not explicitly, but in some form, indirectly learning something, is what allows you to conclude precious information that no other mathematics seems to be able to do. So far, we don't have any other proof of Fermat's last theorem, for example, and many, many other theorems. Here's a typical vibrational mode, and I was going to explain to you what's random about it. I'm running out of time, so I'll just say that what you do when you have a vibrational mode is there's a symmetry here which is clear in this picture, but otherwise you can count how many of these nodal domains are there for such a vibrating triangle, arithmetic triangle. And it turns out that the randomness here is the same as monochromatic waves. So this is a theory of probability where actually the probabilists have not understood this problem yet. What's the zero set of a random nodal domain or of random algebraic geometry? But these things are now being answered in probability theory. And my interest in this is greatly enhanced by the fact that the modular forms obey this randomness. And this is all numerical, and of course, just like with pi, or with like the prime number theorem, what we can prove is a little iota of that, and we're very happy with that. So this is a random spherical harmonic. It's supposed to look like that, and it does. So there's the randomness of that model. And using the most advanced tools here, we can show that the number of nodal domains in this problem goes to infinity with the frequency. I should say that Hans Levy, who was one of the great PDE guys in this department at Berkeley in last century, one of his very last theorems was to show that if you take the sphere, where's that sphere? Yeah. And you look at a spherical harmonic, you can make a sequence of eigenmodes which has only 3 nodal domains. So it's not true that the number of nodal domains goes to infinity because of partial differential equations. It's because of randomness. And the modular forms are behaving perfectly random, and there's even a percolation theory that seems to be obeyed by them. So that's where probability theory is getting to be already quite advanced in understanding these. All right, so let me conclude and go back to Paul Cohen. So firstly, I've been talking about randomness, and establishing the randomness to non-structured number theoretic problems is usually very difficult. And we are happy to prove that pi is irrational or pi is transcendental. And similarly here, we're happy to prove that some randomness feature like square root cancellation in the function field is very powerful. And in the case of lambda n, we stuck. So this, and in terms of applications, there's no question about the use of this kind of number theory. On the other hand, I agree completely with Paul Cohen that most problems that we pose in number theory, and probably in other parts of mathematics, will never be answered. But I absolutely don't share his pessimism, because I think that mathematicians are very good at sifting out what the fundamental problems are. So people raise problems, and the ones that are not approachable and not interesting disappear. But the ones which are approachable get solved. That gets added to our lovely subject. And then occasionally, these real important problems for which anybody in the trenches who's working on these problems are not worried about what can or cannot be proved, though you might be burnt occasionally. Those problems, I believe, we have a great knack of singling out those problems that actually will be solved. So twin primes, I'm sure, will be solved. By the way, I want to make another joke here, is Sarah, who gives fantastic lectures. I heard him give a lecture a few years ago in Princeton, where he was explaining the twin prime problem as unnatural. But then he said unmotivated. And it took me about 2 minutes to realize his joke. Non-motivic, that's for mathematicians. It's a non-motivic problem, unmotivated. He certainly thinks the problem's a great problem. I have no doubt it will be solved. The parity problem is what's keeping us away from it, but it will be solved. And I should say Cohen himself, who put a tremendous effort to the Riemann hypothesis, on most days certainly believed that the Riemann hypothesis itself is something that certainly will be solved. So our subject is very far from drying up the way he said. I don't take his pessimistic view. In fact, we are all very privileged to live in the golden era where some remarkable theorems have been proved. It is the golden era of mathematics. Thank you. Yeah. Yeah, absolutely. So the proof, there are thousands of theorems that say assume the Riemann hypothesis in a somewhat generalized form, and then they imply something, and what that thing they imply is something very interesting, very fundamental, and usually the step that the Riemann hypothesis has achieved for you is some randomness establishment or some control that you wouldn't have otherwise, but usually with some which, if it were random, would be easily handled. And so the answer is, in terms of mathematics, there's no question about its use, but in terms of its outside use, just like the function field, I can give you many. So one reason the Riemann hypothesis sticks out as a problem as opposed to almost any other problem is it's a truth that's so powerful that, unlike the twin prime, I don't know any use of that. It's just, you've got to answer that question. How can you not answer that question? But the Riemann hypothesis is also a powerful fundamental truth about numbers. And it's really saying there's no unexpected behavior that we don't know. It's really saying that parity is random. It's equivalent to the Riemann hypothesis. It's just that's not the way to attack it, in my view. I mean, I should tell you, I get at the annals 6 proofs of Riemann each week. I have to spend a good few hours just rejecting these. But 99.9 can be rejected on the basis of a certain thing, which I'll keep in my, as part of my ammunition. And then there's the ones that, okay, I'll look at it later, and then that poor author has to wait for a long time. So the answer is, it's an unusual, I don't know of any other problem that has such a truth, such a rigging truth that so many other things follow. So it does, but it doesn't say anything unexpected. It says there's nothing unexpected that we haven't. There are no correlations, there's no structure. If you know the number, if you have a number n, a very large number, you have no idea whether it's got an even or odd number of prime factors. If it's got an even number of prime factors, then you say, well, does the next one have some, does that condition the next one to look something? And the answer is no, we don't believe that, and that's what it's saying. And proving something is random, as Paul Cohen said, he was dissecting Skolom's method, saying, well, all you do is this, and then how are you going to prove many theorems? Probably you won't prove many theorems, but the way we win is those little miracles where the problem is somehow natural and wants to be solved. Of course, you have to believe in your heart that these problems are solvable. Cohen did. This was a bad day when he wrote that. It was, you get late in your life and you want to explain why you failed. Littlewood also, by the way. Littlewood, late in his life, started saying the Riemann hypothesis is false. I'm sure it's just simply because he couldn't do it. There's no good reason to believe it's false. Yeah. Yeah. So this is a very good thing. When Li and Yang proved their theorem in statistical physics that the zeros of a certain Ising partition function have all its zeros on a circle, and the function field, when Riemann hypothesis, as it's normally stated, it's about a function, it's about a polynomial, all of whose zeros lie on a circle. So it looks, and Mark Katz and Polya immediately thought this clearly is somehow related to Riemann. The trouble with this Li-Yang theorem, and you it's proved by a method which there's no way you're going to prove the Riemann hypothesis, because the method is, well, firstly, it's constructed inductively. There are many proofs, but one of the usual thing is to count the number of zeros and show that they're all on the circle. And you can see sign changes, for example. There's a version that's used in this construction called by Lieb and Haleman of this Li-Yang theorem. Anyway, that theorem and the connection, I see it very clearly. I don't know that Nikhil sees it. I don't know if he's here even. But the way it's used is in the construction where they prove something called Bilou's conjecture, lineal and Bilou's conjecture, is they take all double covers, which are all plus minus ones of a graph, and they look at all the double covers, and they want to show that there's at least one double cover which is Ramanujan, and then repeatedly take double covers. That's how it's proved. That's how they make their construction. So the first step is to take the expected value over all double covers. And you take this expected value over all double covers, and you get a polynomial, and that polynomial has all its roots on a circle, just like the Riemann hypothesis. I know in the construction, the number theoretic construction, I know exactly where the Riemann is used, and it's used heavily, and it's putting all the zeros on a circle. So in this other argument, you take the average value of these characteristic polynomials, and that has the property because of the Li-Yang theorem. Then you want to show that at least one of those has all its guys in the interval, and that's where the interlacing and all this hyperbolic polynomial stuff enters beautifully. So there are two parts in the proof, and the one part to me is identical. So I don't see any connection between the Riemann hypothesis and the Lee-Yang theorem, but there's enough of a connection that the Lee-Yang theorem and the Riemann hypothesis are the source of the key property in the two constructions. Yeah.
So you've given a few examples.
Very few, and there are hundreds more. There's
of sort of like long-standing conjectures that have either, in the case of Fermat's last theorem, been proven, or the Goldbach conjecture sort of like weakened versions of something proven, or as the Riemann hypothesis remain as yet unproven, but there's a consensus that this somehow must be true. I'm wondering what, to your mind, are the best example or examples of things that were widely believed to be true that were then found to not be true.
We seem to forget those very quickly. Well, most conjectures in Diophantine equations are based on ignorance, meaning we only know how to make integer points or rational points. And in those situations, people have to keep modifying them as people find examples. So it's very dangerous when you say, all right, all of these, usually those mistakes, those false things are somebody has some structure, they prove something, and then they conjecture it's true universally. And then, I know some examples that I was involved with disproving, but I don't want to mention the names. So, and otherwise I'm blanking on big failures of conjectures. Erdős, remarkably, who made millions and millions of conjectures, of which many might fall into this category of not solvable, but his great talent, and this is an immense talent, is he always, usually is right, sometimes wrong, but usually right, but he knows how to put it just out of reach so that you become addicted. And so that you say, wait, I can do that. And most of his conjectures that I know, there's so many of them but every now and then somebody will come and give a talk and say, I've solved this conjecture of Erdős worth $2,000, and that gives you some clue of how difficult it was. Anyway, his great ability was, I think, to find truths which are epsilon away from what actually can be done and require a new idea to solve it, so it enriches the field in that way. But I've heard a lot of criticism about that kind of mathematics. In fact, Cohen would criticize that kind of, hundreds of different problems, and it's a bit like math competitions. So I think that in terms of the main problems, mathematicians are very good at sifting out, kicking it around, and then what remains. And we've seen, Fermat's last theorem, but we've seen something even greater, the proof of the Poincaré conjecture. We live at a very special time.
Good point to stop. Join me in thanking Peter, Professor.
Thank you. Okay.